So we're going to start with heuristic search methods. So things that search like A star. We're going to go to motion planning, and then we're going to do a lazy search, which is more efficient ways of doing search. Finally, we'll go to learning. We'll cover some imitation learning. Then we'll cover RL methods, model-free, and model-based. Right? And I'll hopefully give you some perspective, and we'll have 2 guest lectures at the end. Yeah. Okay, so that's what we're going to do. Some logistics before we get started. I sent out emails at some point last night with all the teams and workstations and cars assigned. Let me know if anyone didn't get an email from me. That's a mistake. And we'll assign you to a team. Now that your teams are assigned, just reply to that email with the name of your team. Be creative. And we'll help you make a repo and get started. And we'll release project 1 tomorrow. And you'll have around 10 days to do it. You don't need the car to do project 1. It's all in simulation. Right. And then we'll have car pickup next week on Tuesday and Wednesday. There'll also be a little tutorial on how to use the cars, how to be safe. So do come to those. Okay. Any other questions you guys are having, post on Ed. If you don't have access to 002 in Allen, let us know. We should have access for everyone registered for the class. Go ahead.
The current project that's released on the website.
Well, the problem is that it's released, but you don't have access to the code right now anyways. So I would say I'll send an announcement tomorrow morning with all of this stuff. It's going to be that project, but we'll just set up the infrastructure. Okay. Cool. That's all the logistics. Any other questions, concerns, things that we should address? Okay. 002. Yeah, the basement. Great. So a little bit of a recap. Last class we covered helicopter design going from sensors to actuators with a combination of state estimation, world modeling, and then planning and control. Today we're gonna start by instantiating state estimation and like cover some of the basics. But some context before that, which I didn't get through last class, is we were talking a little bit about end-to-end learning. So the model-based way of doing control is saying, let's estimate where we are. Let's then model how the world will evolve, and let's use that to plan, or let's use that for decision-making. The end-to-end method says, let's take in sensors, big neural net, actions come out, right? And so we talked about 2 different ways to do this, imitation learning and reinforcement learning. There's other ways to do it too, but those are the common ones. And the point I kind of wanted to get to is why do we want to do this, or when do we want to do this? So do people have guesses on why you would want to do learning? What are the advantages of doing an end-to-end method? An end-to-end method doesn't define these interfaces, it's just data-driven. Yeah.
It's hard to model.
Problem that's hard to model.
It's computationally expensive and much easier.
Right. Computationally expensive and hard to model. Good point. Other thoughts? Yeah.
It's also just like pretty nice for and more to the point of not being hard to model. Maybe your assumptions or like the rules you set for your role model are inaccurate or incomplete.
That's right.
You can capture more generalities.
That's right. So it's like it overcomes any bias in your model because you're using that like true data from the environment. So modules can kind of compensate for each other. So if you have, for instance, a modular system that estimates state, then there's modeling, then there's decision making. The modules might have like no way to compensate for each other. So if you have error in your state estimate, it might totally screw up your model. Whereas if it's end to end, you kind of like have things account for each other, right? You're avoiding hand designing interfaces. So one thing that's tricky for something like manipulation is like, what is the state of this bottle? Like, what is 0, 0? What is this axis that you would follow, right? So, and like, it's even harder for like deformable objects. Like, how do you even define state? And so, like, avoids those kinds of things. And it often does better because it avoids bias. But why might it be not always desirable?
Because your model is mostly doing the heavy lifting for you. It's sometimes pretty hard to understand what it actually.
Interpretability, yeah, interpretability is a big deal. Yeah.
I guess we talk to generalists if you're in a very specific.
Right. tough to generalize. Whereas like physics is general by construction. Other thoughts? Both of those are valid, yeah.
We need to actually have the data.
You need to have the data.
It's not always that.
It's expensive to get the data. Yeah, good.
I was gonna say reproducibility.
Reproducibility, yeah. If you have 3 different random seeds, it does different things. So all of those are completely valid. So a little hard to see, but lack of interpretability, lack of reusability, data efficiency, amongst other points, right? Yeah, but I think if you have a safety critical application, use a model-based method. If you have like an application that's really hard to model and kind of lower stakes, you want to use data-driven. That's how I think about it. Okay. Our quiz for today is what is the difference between planning and control? Do that real quick before we keep going. The options are discrete versus continuous, coarse versus fine grained, human defined versus automatic, none of the above. Don't think too hard about it, it's fine. I'm not going to check for correctness. Okay, everyone done? Anyone still needs a second? Okay, let's keep going. So what our topic today is going to be is let's try to get into what state estimation is, why it's needed, and let's try to build up the mathematical tools we need to do state estimation, right? So the structure of our class today is going to be, we're going to define what state estimation is, why it's needed. We're going to do a little bit of probability review, and then we'll try to use that for Bayesian filtering, right? Okay, so the objective today is going to be, let's try and understand what it means to estimate state. Let's define what state is. Let's define what estimation means, and let's define what let's define the problem more formally. So to motivate this, here's an example from this tour guide robot that Peter Fox, if you know him, who's a professor here, kind of did back in the 90s, which is a museum tour guide robot. So they had a robot that was like guiding people around the museum. And the tricky part is that it has to localize itself in crowds of people. And so what they did is they had the camera pointed at the ceiling, and they would have it like basically figure out where it is by localizing itself with stuff at the ceiling. But you could see like this kid is if you had something that didn't estimate state, it would be a big problem. And so a lot of the pioneering work in this area was done by Dieter and his colleagues, and kind of was applied to these kinds of systems. All right, so we talked about this tour guide robot. It's going around an environment which has noise, disturbances. People are moving it all around. It's big. The exhibits are changing, right? And so, in some sense, it's like hard to know exactly where you are, just by measuring, where you want it to go. And so you kind of have to estimate state. This is often what happens with your Roomba too. I don't know, my Roomba gets lost all the time, but it really should be estimating where it is and acting accordingly. Right? So it's kind of why we're solving that problem. And so the problem of state estimation is saying that given a stream of measurements and actions, estimate what is the probability of your robot being in a particular state. Right? So it's like when I say estimation, you don't know what the state is going to be, but you can estimate a probability distribution over the state. And so the goal is, remember, you're not given any state. You're only given measurements and actions, and you have to estimate state. So you're given measurements, C, actions, U, and you have to estimate distribution, U over S. Yeah. And so like this is the box we're going to try and fill in today. Right? So remember, like state is where you are, right? We'll define what state is, but state is kind of intuitively, state is where you are. Measurements are like your sensor readings, your LiDAR, your sonar, your camera. Your actions are like where you told it to go, and you're going to try and use your measurements and actions to estimate a distribution over state. That's the basic problem. Yes? Questions? Make sense? Good. All right. So what is state? Right. So state is a bit of a vague term because you can't really say what state is in a universal way. But the way I think about state is it's like a sufficient statistic of your history, which is necessary to predict the future and make decisions, right? So it's like, it's telling you, it's describing things about your world that are necessary in order to make decisions about the future. And so for instance, for let's say a robot arm that looks like this, your state might be your position, your velocity, and the force on different like joints, right? For a mobile robot, it might be your position and your orientation, and maybe a few things about the environment, right? But basically, to kind of think of a state as something that you define, which is what you need for decision making, right? And so your state is like a low dimensional entity, which is telling you if I do this thing, I could make decisions about the world. If I'm trying to navigate the world, I need to know where my robot is, right? So in mobile robotics, you often think of state as position and orientation. In robot manipulation, you often think of state as position of all the joints, velocity of all the joints, positions of the objects, and that would be what state estimation is, right? And so it depends on your specific problem, but some examples of state could be pose of a robot, so position, orientation, X, Y heading. It could be configuration of a manipulator, so where the joint angles are, things like positions of the objects in an environment, right? And so I wouldn't take a very rigid notion of state. It's something that you define, but it's super important because you are not given state. You're just given measurements. But state is underlying your system, right? So you're trying to figure out state so you can make decisions in the world. Okay. Does that kind of parse? So all that a state is like the underlying variables of your system that will help you make decisions. Could be position, could be orientation, could be forces. Okay. You have a question?
So, so you have like a base volume robot. Would the location of the walls and the absence of be part of the state, or would that be something that's?
Great question. So you can have a system where you're told the map. And if you're told the map and the map doesn't change, then it's not part of the state. So think of state as things that change, right? And if you're told the map is part of the model and not part of the state, but if the map is unknown and you're trying to figure that out, then it's part of the state. And if the map is changing, then it's part of the state. Right? And so it's really a choice how much you put into the model versus into the state. But typically you want to put the variables that change and are relevant to decision making into the state. Like for instance, whether where the birds in the sky are flying, it's changing, but it's not relevant to decision making, so it's not part of your state.
How did the state change?
Over time, typically you would not have the size of the state change over time, although you could. You typically define it as a fixed set of variables. Yeah, so like in some cases you do padding, so you just take like pad it to the maximum set of objects and then say that some of them are missing. But you could have variable definitions of state. It just like breaks some of the machinery that is conventionally used, but nothing in the system prevents that from being the definition. Good question. Okay. So there's no restriction on states to be, static or dynamic or discrete or continuous. It just depends on your problem. But your goal is to figure out what the state is going to be because your world model takes in the state and predicts what the next state is going to be. Right? Okay. So given our definition of state, what is a measurement, right? So a measurement is a reading from your sensor that provides you information about the state. Right? So for instance, your car is moving around, your measurements would be things like your LiDAR readings or your camera images. Now, LiDAR is not equal to state. LiDAR is just some noisy measurement, which might have something to do with state, but LiDAR is not equal to state. So remember that measurements are not equal to state. Measurements have something to do with state, right? And so some examples of measurements could be GPS, right? GPS is still noisy, it's not perfect. Laser scans, so things like LiDAR, where you shoot a laser beam and try to tell the distance to different obstacles, would be a measurement, or camera image might be a measurement, right? None of them tell you exactly what the state is going to be, but they all give you information about the state, right? And so typically when you think of a measurement, it's something from a sensor that has information about the state, but is usually noisy and is usually not complete. Right? Does that make sense? Okay, so we're not going to be prescriptive about what the measurement's going to be. Different measurement systems will have different models, but we're going to kind of keep the measurement as generic for now. And action is what you'd expect. Action is what moves the system around. So for a car, it would be something like steering and throttle, which says, okay, you're going to move forward, you're going to turn. And that's what kind of transitions the system from one state to the next, right? So in your world model, you're going to take in the state, you're going to take in the action, it's going to give you the next state. So actions are things that changes the state from one time to the next. So some examples of actions could be, forces applied by the robot, so motor currents, torques, throttle, steering. And you could even have no op be an action, so like do nothing, right? But the important thing is that action is also defined by you as a robot designer. You can choose what the action space is going to be. You can choose the action space to be lowest level currents. You can choose the action space to be positions to move to. You can choose like different choices of actions will work, right? So it's like a choice. Okay, so given these definitions, we're going to call state X, we're going to call action U, and we're going to call measurement C, right? And so what you're going to observe is a series of measurements and actions, and you never see the state, right? And you're going to try and estimate what the state is going to be from this series of measurements and actions. You're going to try and figure out a distribution over X. Okay? And that's going to be called your belief. Yes? So think of distribution over X. Given basically your belief is your distribution over X at some time step T, given your actions until that time and your measurements until that time. Okay? So that's the problem we're going to solve is we're going to try and figure out P of XT given U1 to T and Z1 to T. Okay? Good. Okay, so that's what we really want to solve. The difficult problem here is that you don't exactly know the mapping from Z's to X's, and it's noisy and it's incomplete, right? And the other problem is, let's say you move your system, there's going to be noise when you move your system, right? You applied some controls, there'll be some external noise, there'll be some slip. And so there's going to be noise in taking actions, and there's going to be noise in your measurements. And so this whole process has to account for all the noise and deal with it. And so that's what makes state estimation hard, right? And so we're going to define this notion of belief. And so all of belief is going to be is a probability distribution over state xt at some time, given measurements z1 to t and actions u1 to t. We're going to take your history of measurements, your history of actions, and try to estimate the current state. And so history of measurements, history of actions, and then estimate the current state. Yes. So you'd often call this a posterior, right? You're trying to say, you're trying to get a distribution over this. You're trying to get a distribution of something given evidence. You can have different forms of like how to represent this. You can have your distribution be a table. You can have it be, some continuous probability distribution. You can have it be a histogram. You could have it be a diffusion model, right? All of those kind of hold. But we're going to discuss a few concrete choices. Does this problem make sense? Okay. So why should we be probabilistic? Right. So if I wanted, I could just take U1 to T, Z1 to T, and map to a single XT. The tricky part is that our measurement model, the thing that gives us measurements, is noisy. Our motion is noisy. You're going to take an action, it's going to be noisy. And if you're able to be probabilistic, then you're able to not just measure the most likely state, you're able to measure, how uncertain you are. And so it's useful to know how uncertain you are because that can determine how you act. Right? Like for instance, if I'm really uncertain, I might want to go collect more information. And so uncertainty allows me to do that. It allows me to say, okay, I'm really not sure where my car is. Probably shouldn't be speeding at 100 miles an hour. And so it allows us to kind of deal with uncertainty and incorporate that into decision making. So whenever you think about, there's a textbook called Probabilistic Robotics, which is the recommended course. The whole thing is about how do we be probabilistic in state estimation, in planning, in control, so that we can deal with, the inherent noise in our system and kind of incorporate uncertainty into our plan. Right? And so the way I think about it is noise is a good way for us to deal with the models being inaccurate, the hardware being inaccurate, the world being inaccurate, and like act in a way that's safe. Right? So being probabilistic helps to be safe. Good. So if you're not able to, estimate state, there's a method called dead reckoning, which says that I'm just going to trust that my model is going to be correct. I'll think where I am initially, and then I'll just kind of like, act according to, like, I'm not going to take sensor readings from the world. I'm just going to act according to where I thought I was, right? And so you can see here, it's trying to go in a square. But if you let it go for a little while, you'll see that it starts to drift, right? And so this is an example of a dead reckoning system where you're just saying, okay, I'm going to like measure how many times my wheel should turn, but there's going to be slip in the system, and that's going to kind of change where the robot is going. And because it never takes measurements, you can see that like over time, it's going to like drift off. It drifts off at some point. Yeah, it's doing crazy stuff. But you'll see that your system drifts off. So like first time I was ever doing Lego robotics, we did dead reckoning, and it was just terrible. Go ahead.
If you're doing dead reckoning, does that require that you like are going like predefined?
So you don't have to go on a predefined path. It's more like it's like you start from where you think you are, and then you continue to act in your model with never going back to the real world and using sensor readings. So you can like make decisions on where you think you are, which might be a variable, but where you think you are is never getting updated by sensor readings. Yeah.
Why?
I think sometimes if you don't do state estimation well, it can be worse than dead reckoning even because your like measurements, if they're inaccurate, can like cause your system to do even worse. And so if you have like a faulty sensor or something like that, then that might lead to worse performance than if you just didn't measure it all. But in most cases, no. Okay, so typically when we're going to be talking about probabilistic robotics, it is trying to do explicit representations of uncertainty and use that for decision making. When we say the word perception, that means usually state estimation, and action is trying to use our estimate of state to optimize utility or optimize cost under some constraints. Okay? So that's kind of going to be our definition of state estimation. State estimation is just P of xt given u 1 to t and z 1 to t. And I solve that problem. Yeah, good. All right, so how familiar are people with probability? Have people done a lot of probability before? Thumbs up if yes. Ish. Okay, so probability review is good. Should we do it? Yes? Or is it a waste of time? Good? Okay, let's do it. So we're going to brush up on probability. So when we think of probability, you have random variables. Let's say a random variable is like an event that can happen in the world. We're going to denote these by these capital letters, A, B, all of these are random variables, right? And you're trying to think of the probability of an event happening, right? And probability of a discrete event always lies between 0 and 1, right? The probability of the complete set of all events, so let's say the switch could be on or off, right? The probability of a complete set of events is 1, right? And the probability of a null set of no events is 0, right? And the probability always lies between 0 and 1. And if you have the probability of two random events occurring, A union B, is probability of A plus probability of B minus probability of both happening. So you don't double count. Right? So it's kind of like A, B. When you're taking the union, you take A plus B and you remove one double count. And so Probability of A is the probability that you have a particular outcome. A and B are events. Omega is the set of all possible outcomes, and phi is the null set, right? That's the notation we're going to use. So those are just some fundamental axioms. From those fundamental axioms, you can kind of get corollaries that make sense. Let's not worry about the derivation too much, but really all that is saying is that if you have this backwards arrow, this is what you'd call the complement, right? So if it's saying what is the likelihood that A does not happen, right? So if you have the likelihood of A as probability of A, the likelihood of A not happening is 1 minus the probability of A. Okay? And so the logic is just that the probability of A plus probability of not A is equal to 1, right? Because either A happens or A doesn't happen, which means that the probability of A, probability of not A is equal to 1 minus the probability of A. Yes? So, so that's just saying something is a complement. And the probability of A union B, if A and B have no overlap, is probability of A plus probability of B, right? And so how do we derive that? Like, given everything that we've seen so far, how do we derive the probability of A union B if A and B are have no overlap is probability of A plus probability.
Probability of A in, or like the overlap would be is 0.
Yeah. Perfect. Perfect. So you basically use this identity, and this is basically 0. Remind me your name? Marco. Yeah. As Marco was saying, basically probability A and B is 0, or basically A and B is the null set, which means the probability of that null set is 0. So probability of A union B, if A and B are non-overlapping, is A plus B, right? Okay, so those are some simple ones. Now you can have different types of probability distributions. You have things that are discrete and things that are continuous, right? So the typical ones you'd first hear about are discrete, right? So if you have a discrete random variable, it can take on a countable number of values. Right? So you have a finite number of values that it can take on, right? And you're going to say that like your probability of x equal to xi, where xi is a particular outcome that it can take on, is the probability mass function. Right? For continuous values, it's going to be the probability density function, but for discrete, it's going to be the probability mass function. And you're going to use the shorthand of P of xi as probability that the random variable x was equal to xi. Yeah. So whenever I use P of xi, I mean probability that x was equal to xi. Okay. And so, for instance, the probability that I was in one of 4 rooms could be a table which looks like probability that I'm in room A is 0.7, probability I'm in room B is 0.2, probability I'm in room C is 0.08, and D is 0.02. Like that is a valid table because this whole thing sums up to 1. All of them are between 0 and 1, right? And so it's a valid probability. It's a valid discrete probability distribution. Right? So think of a discrete probability distribution as just a table. And so you're just saying this is a table. Table values have to be positive and between 0 and 1, and they have to sum up to 1. Okay, so that's discrete probability distributions. Lots of different examples. Some of them are binomials, where you flip coins and you count how many heads you got. That's a binomial distribution. Multinomial distribution is you toss die and see how many of each number you got. Bernoulli is flip a coin and see whether it's head or tails. And Poisson is things like how many events happened within in a period of time, right? So there's different distributions. We'll cover the ones we need when they come up. But all of these are just different examples of probability distributions that are discrete, right? Now, you also have continuous random variables, right? So you have a continuous random variable, let's call it capital X. It takes on a continuum of values, so it's an uncountable number of values, right? So it's saying that like X can be anywhere between 0 and 100, but it doesn't have to be integers, right? It could be a continuum of values. And we're still going to use the shorthand of P of X to denote P of capital X is equal to small x, right? So small x is the outcome, capital X is the random variable. Yeah. And we're going to say that that is a probability density function. Now, the important thing to know about a probability density function is that it doesn't have to be less than 1. And so probability density function is potentially greater than, it still has to be positive, but it doesn't have to be less than 1. It just has to integrate to 1. Right? So you're saying that like probability density P of x dx over the range of whatever values has to be equal to 1. Right? But any individual number can be greater than 1. It just has to integrate to. Right? So don't get confused by probability density being greater than 1. It just has to integrate to. Whereas in a discrete variable, probability mass cannot be greater than 1. Yeah. Okay. Does it make sense? Discrete, continuous probability distributions. Are we comfortable? Some basic A plus B is equal to, or probability A and B is A plus B minus the intersection. Like, and the complement is 1 minus. Really, that's kind of all we need from here. Yeah. So lots of different examples. You have Gaussians, which are probably the most common. You have things like the beta distribution. You have other forms of continuous things that'll come up. But we don't need to memorize them. Okay, so given these basic notions, let's go over what joint and conditional probability mean, right? So when I say joint probability, I mean that if there's two different random variables, x and y, what is the probability that capital X was equal to small x and capital Y was equal to small y, right? So when I have two variables inside a probability, that is the joint probability distribution. So P of x comma y. So it's like saying, what is the chance that I was in California and it was raining, right? And so you want to see what is the likelihood of two different events happening. And so if you have two events that are independent, right? So you can define events as independent. If the likelihood that P of x happened and P of y happened is just equal to the probability of them happening independently. Right? So they're like not dependent on each other. Like, for instance, if whether I go to California may not affect whether you guys go to California, and those would be independent, right? Or whether I go to California may not affect whether the Dodgers win the World Series or whatever. And those would be independent events, right? So events are independent if you can say that their joint probability is equal to the product of their individual probabilities. Right? And so if you ever find that P of x comma y is P of x times P of y, then those are independent, right? This is not true in general. It's only true if those events are independent. What is true in general, though, is that if you have the joint distribution between two random variables, P of x comma y, you can write it as P of y given x. My x's and y's look the same, sorry. P of x comma y is P of x given y times P of y, right? Or you can also write it as P of y given x times P of x, right? So the likelihood of two events happening is equal to the likelihood of the first event happening and then the likelihood of the second event happening given that the first event happened. And you can order them either way, right? And so this is super important. Whenever you have a joint probability, you can always write it as P of x given y times P of y, or P of y given x times P of x. Yeah. And so whenever you think of a conditional, so you think of this thing as a joint and this thing as a conditional, right? So remember that you can always write the joint as the product of P of x times P of y given x, or the other way around. You'll call this the marginal. You'll call this the conditional. Yes? So just think of this as saying, if two events were to happen, it's the likelihood of the first event happening and the likelihood of the second event happening given that the first event happened. Okay, so that's the joint probability. And if x and y are independent, then P of x given y is equal to P of x, right? And so this is saying that like whether or not y happened has no bearing on whether x happens, right? So P of x given y is the same as P of x. And this kind of passes our smell test because it says that, if P of x comma y is always equal to P of x given y times P of y, but if x and y are independent, then P of x given y is the same as P of x, right? That means that this joint distribution just becomes P of x times P of y, right? Because this and this were the same. Yeah, so it like passes our sanity checks. Make sense? Confused? No? Good? Okay. If you guys don't speak, I'm going to assume that everyone gets it. Or I'll repeat it too much. So please speak up. Okay, good. So that's some basic things about joint and conditional probability. You can also say a few things about a law of total probability. So in a discrete case, the sum of P of x over all possible values of x is 1, right? Like one of those values has to occur. This one is an important one. It's saying that like if you have a joint distribution P of x comma y, if you sum it out over one of the values, it's going to be equal to the P of the other one. So it's like if you have P of x comma y and you sum it up over y, that'll be equal to P of x. So you're kind of like, if you sum it up over one of the variables, you're eliminating that variable, right? And so that's how you like, that's often what you'll call marginalizing a joint distribution. You're going to take a joint distribution and you're going to sum it up over one of the variables and it's going to marginalize it. And so whenever you have a joint distribution and you want to get the distribution of any one of them, you just like sum out one of the variables, right? So it's kind of saying that like what you can kind of, we'll go through some intuitive examples, but basically it's saying that like, if I want to get the distribution of x happening, you sum up you want to get the likelihood of x happening, you sum up the likelihood of x happening along with every possible value of y. And that covers all of the ways that x could have happened. Right? And so you can just use the previous definition of joint that we had to convert this to this, because we know that the joint is P of x given y times P of y. Right? So there's one thing about probability that you should remember. There are two things about probability that you should remember. One of them is that the joint is a product of the marginal times the conditional, right? This is what you call like the chain rule of probability. And the second is that if you marginalize, if you sum up a joint distribution over any one of the random variables, it's going to be equal to P of the other one, right? You can extend this to like multiple variables. Does this parse overall? Questions, confusion? Because otherwise, if it doesn't parse, the next section is going to make no sense. Okay. And you can do the same thing for continuous variables. You just replace sums with integrals, and everything else holds, right? So let's do a few exercises, right? So this is our table. This is our joint probability table. It's saying the two random variables x and y, they could be positive or negative. The probability is on the right. Gives a valid probability distribution. Yes? Yes? Because they're all positive, they're all between 0 and 1, and they sum up to 1. Right? Now, let's try to answer these questions. What is P of plus x comma plus y, given this table? 0.2, right? So you're just going to look this entry, right? And P of plus x comma plus y is just going to be 0.2. Right? It's the likelihood of both of those events happening. The table tells it to you. Now, what is the likelihood of P of plus x? Yeah. P of plus x is 0.5, and tell us why.
This is some of the first two rows because it's the probability, you don't care about what happens.
You don't care about what happens with y, right? So you're going to say, I'm going to consider plus x no matter what happens to y. So I'm going to consider this row and I'm going to consider this row, right? And this is what we were talking about with marginalization, right? So you're going to take the joint distribution and sum up over no matter what happens to y, right? So you're going to say it's going to be 0.2 plus 0.3, and so it's going to be equal to 0.5. Yes? Okay, and what is the likelihood of minus y or plus x? 0.6. Tell us why.
Plus X. Just
Yeah, exactly. Right. So you're going to take, you basically, the way I think about it is like take any row which has minus y or plus x, And the key is you just need to avoid double counting this guy. Right? And so this is going to be 0.1 plus 0.3 plus 0.2, which is 0.6. Yes? This kind of makes sense? Good. Alrighty. Now let's think about marginal distribution, right? And so if I have this table and I want to construct a table over just what P of X is going to be, I can say P of plus X is what? 0.5. P of minus X is what? 0.5. And you can kind of do the same thing for Y, right? So Y is going to be what? Y is going to be plus Y is going to be 0.6 and minus Y is going to be 0.4, right? All right, I think you guys get it. But you can kind of think of it as you took this table and you summed up the variable that you're trying to remove, right? As you're trying to eliminate that variable. And now let's think about conditionals really quick. What is P of plus X given plus Y? Plus X given plus Y. So tell us why.
Oh, wait, no.
Yeah, right. So if you want to get P of plus X given plus Y, you're trying to find out the likelihood of X given that you got Y, right? So look at all of the entries that have plus Y, right? Which is going to be 0.2 plus 0.4. And then you look at amongst them, like what is the likelihood you get to plus X, right? So you're going to you can kind of write P of plus X given plus Y as P of, you can write it as P of plus X comma plus Y divided by P of plus Y. So whenever you, like, if you remember the definition of the joint, you can write this as P of X comma Y is P of X given Y times P of Y, right? Which means that if you have the conditional, you can always write that as the joint divided by the marginal, right? And so in this case, our joint is going to be 0.2 because it is the likelihood that you got both plus X and plus Y. And our marginal is going to be 0.2 plus 0.4, right? Which is going to be 0.6. So it's going to be 1/3. Yeah. And so whenever you're trying to get a conditional, think of it as taking the joint and dividing by the marginal, right? So take P of X comma Y and divide by P of Y. Another way of thinking about it is take the rows that have plus Y, and then that's going to be your denominator, and take the rows that have plus X and plus Y, and that's going to be your numerator. Okay, so we've established this is 0.33333. What are the other ones? Yeah. Minus X given, yeah, 0.6666, right? For the same reason, the other way of getting this is you know that this is 0.333, and you know that this is the complement of this, and so you can just do 1 minus. Right? And last one, what is P of minus Y given plus X? 0.6. So P of minus Y given plus X is going to be, you're going to take plus X here, right? So these two rows, and then you're going to see what is minus Y. So your numerator is going to be 0.3. Your denominator is going to be 0.3 plus 0.2, right? It's going to be 0.6. Yes? Does this parse? So whenever you have a conditional, think of it as a joint divided by a marginal, right? And you can kind of derive all of these from the same thing. I don't expect you guys to be experts at this immediately. Just kind of mess around with it a bit and get comfortable with it. Cool. Alrighty. So this kind of brings us to arguably the most important formula in all of probability, which is the Bayes rule, right? The Bayes rule is super easy once you've established all of this background. But what the Bayes rule says, one way of thinking about it is the Bayes rule tries to convert from y given x to x given y, right? And so the way you can derive the Bayes rule is to say that when you have a joint distribution, you can write it as P of x given y times P of y or P of y given x times P of x, right? And now if you want to convert from one to the other, you just like move one of them over to the other side or move one of them over to the other side, right? So what I mean is, let's say P of x given y times P of y is equal to P of y given x times P of x, right? Let's divide both sides by P of y, right? So divide both sides by P of y, these cancel, and you get this, right? And so what Bayes' rule says is that P of x given y is P of y given x times P of x divided by P of y. Yeah. And so this is often called your likelihood. This is often called your prior, and this is often called your evidence, right? And so like you'd often call this your posterior. These terms don't matter that much, but all like the way to think about Bayes' rule is it's trying to say if I knew how likely y was given x, can I say how likely x is given y? Okay. You're just trying to flip it. And so the way it's going to apply to Bayesian filtering and robotics is if I knew how likely a measurement was given a state, then I know how likely a state is given a measurement, right? And so you're going to try and use Bayes' rule to kind of flip measurements. So if I knew the probability that I would get a measurement, that when I get a measurement, I can know what the probability of the state is. Right? So you're trying to say, you're trying to like essentially flip evidence. And so what Bayes' rule is trying to do is just trying to flip evidence. We'll go over some examples to make this more clear, but just remember, whenever you have Bayes' rule, it's always trying to convert P of y given x into P of x given y. Right? And if you ever forget Bayes' rule, there's a few ways to remember it. You can derive it by just matching P of y given x times P of x to P of x given y times P of y, rearranging the terms. Another way of thinking about it is the numerator is just a joint between x and y, right? And so you can say P of x given y is the joint between x and y divided by P of y. Yeah. Okay, so an example of Bayes' rule is this table of symptoms in cancer, right? So it's saying you know the likelihood of like getting symptoms if you have cancer. You know the likelihood of cancer. What is the likelihood that you have cancer if you had symptoms, right? And so let's try and work this out. But basically, P of cancer given symptoms is equal to P of symptoms given cancer times P of cancer divided by P of symptoms, right? And so let me scratch this out so you guys can't see with my excellent scratching skills. Now, let's work it out. There's usually a way I can cover things, but let's try and work out what this is going to be. P of symptoms given cancer is what? 1, right? Because if you look at this table, if I have cancer, I always have symptoms, right? So this is going to be 1. What is the probability of cancer? It looks like 100,000 to me. Yeah. So probability of cancer is 1 over 100,000, right? So 1 e negative 5. And so your numerator is going to be 1 times 1 e negative 5. And your denominator is going to be P of symptoms, which is essentially going to be the probability of symptoms given cancer times P of cancer plus the probability of symptoms given no cancer times the probability of no cancer, right? And so the denominator is going to be 1 times 1 e negative 5 plus the probability of symptoms given no cancer, which is going to be 10 divided by 99999, right? So this is the likelihood that if you didn't have cancer, you would still show symptoms, right? So there's some likelihood that you would show symptoms even if you didn't have cancer, and multiplied by the likelihood of not cancer, right? So you can work through the algebra, and it comes out to 9.1%. But that means that just because you have symptoms doesn't mean you have cancer. So don't WebMD yourself. You'll be okay. So that's what Bayes' rule is, right? It's generally trying to like convert evidence into diagnostics. right? And so next class, what we're going to try and do is we're going to try and use Bayes' rule to do filtering, which means that we're going to try and figure out where the robot is, given the evidence we get from the world, right? All right, see you next time.
Spend like 2 weeks on this.
You guys spent 2 weeks on this?
Probably. Yeah. That's where they're right.